Quantum science is the physics of smallest scale. Quantum information science deals with acquiring minuscule amount of energy or information from quantum systems utilizing quantum sensors. And we can harness those to look for certain phenomena, signature, or dark matter in our case. Hello, everybody. I'm Raksha Khatiora. I'm a professor at Illinois Institute of Technology, and I'm also a scientist at Fermilab. I work on dark matter detection using quantum sensing. So today I'll be talking about what quantum sensing is a little bit, and I will take you in a virtual tour of our facility, our lab at Fermilab. And you'll also hear from a couple of our scientists there in my group.
One of the problems plaguing the quantum information science community is that the fundamental bits of a quantum computer are very sensitive to environmental noise. And that's a problem for them because you really want information to be retained so that you can do all of your calculations and so on and so forth. But one of the really nice things is that if you turn the coin over, it means that those sensors are potentially, or those fundamental, we call them qubits, fundamental elements of quantum computers, those may be more sensitive to certain kinds of interactions, say dark matter, than other detectors that we have built are. And so the idea behind this group and this group's efforts is that we want to take the massive amount of progress in the quantum computing field over the last few decades, and turn that into, flip it on its head, and turn that into a potential detector or sensor for dark matter scatters in the lab.
So sensing is basically acquiring information that you want, right? So quantum sensing is detecting extremely small amount of energy, magnetic field, temperature, anything that you're measuring with quantum technology and tools. So that's kind of how I would define it. And so you probably have heard of qubits, which are these artificial atoms, and also the building blocks of quantum computers. These are the broadly used quantum sensors, and that's what we use to look for dark matter and detect dark matter.
A sensor is something that can take a signal of energy and transduce that into something that a computer can process in the most general sense. And so that might be something like you've got a target material, so some crystal, and you've got dark matter or some other particle coming in, and it slaps an atom and produces some charge or some vibrations in the crystal, and you want to read those channels, either the charge or vibrations or whatever it may be. You want to read that out and digitize that signal and do some analysis on it to learn about the particle that came in and slapped your target.
Quantum sensors have advantage over traditional sensors in mostly two ways. One is they have extreme sensitivity to measure any physical observables that we discussed, like magnetic field, temperature, energy in general. On the other hand, they also have advantage over how fast the measurement can be done. So typically the quantum sensors would be able to do the same sort of measurement, get to the same amount of sensitivity in an extremely small, shorter amount of time compared to a traditional sensor.
We're talking a little bit about dark matter direct detection. We want to build a detector in which the dark matter particles can scatter, and then we can see it. The kind of sensor that we want to use, again, is from the quantum information, quantum computing field. And what that looks like is actually a very small chip of either silicon or sapphire with some superconducting metal plated onto it. And so if you look in here in the center square, you can kind of see a little bit of reflective chip. And that's effectively our detector. And it has 6 qubits on it, and those qubits can read out or sense the very may be able to sense the very weak interactions that arise when dark matter bumps into the chip material. And then, of course, the chip is kind of installed in a housing that keeps it cold, and it extracts heat from it so that we can see the small amount of heat that's deposited when a dark matter particle scatters. And then there's a bunch of cabling that allows us to talk to the chip and read out the information from these scatters. And then all of that is inside this kind of cylindrical can here, which kind of provides magnetic shielding because the sensors themselves, the qubits, are very, very sensitive to magnetic fields. And so by surrounding it with this can, you can kind of expel magnetic fields and keep that inner region very quiet in terms of magnetic field.
All the qubit devices are housed in this refrigerator. So this is not your regular refrigerator. This is called dilution refrigerator. And so it's one of the coldest refrigerators out there. It cools everything, all these devices, sensing devices, very, very close to absolute zero, which is the coldest temperature we can have in the universe. And so everything is at room temperature on top of the fridge. And so all these different plates that you see in the fridge correspond to various temperature stages in decreasing order. So you are going from room temperature to slightly colder on top there, even further colder down here, and then the coldest being here. So this temperature stage is very, very close to absolute zero, which is 0 Kelvin. So this is like a few millikelvin we are talking about. So very, very close to absolute zero. And so this is work of art, and it has taken engineers and scientists decades of work to come up with this kind of dilution refrigerator, because it's extremely difficult to get anything this cold to absolute zero, this cold close to absolute zero. So here what you are seeing is the sensing devices based on qubits housed in this plate over here. So this cools this device to very, very close to absolute zero. And as I mentioned, we do want the devices to be physically very cold because we want to avoid these background photons that is not good for our dark matter experiments and other sensing, like fundamental science experiments. So we want to cool this like this. And so here you can see other accessories also installed in this refrigerator. So the main idea is we sent out some known signal from top of the fridge. It goes to the qubit-based devices here, and then for sensing purpose, we can get information about the state of qubit by looking at the signal that comes out back. So whatever we send in, it changes a little bit depending on the state of the qubit, and we read it out back, and that signal that we read back will tell us, did the qubit state change? And the qubit state, if it changed, that means you had either dark matter activity or some sort of background that changed it. And so that's kind of like the core of like sensing. That's how we do sensing with qubit devices. You saw earlier the warm refrigerator. It was open. It had been open for us to populate with the electronics, the qubit-based quantum sensing electronics. So here is an example of how it looks when it's cold. And so of course you can't see the inside, right? Like, so there's a shield here, and right now it has a bunch of qubit-based quantum sensing apparatus inside, and it's cold. It's about 10 millikelvin or so very, very close to absolute zero.
Dark matter is produced very early in the universe, and so once we start to understand how dark matter interacts, we can then look back and say, okay, given how we know now, from what we can see, how it interacts, what effects that would have had on the early structure of the universe. And so I think what's really interesting about dark matter is the fact that like none of this stuff exists without dark matter, because in the early universe you have these minor fluctuations in density. Dark matter is there's way more dark matter than there is regular matter, and so you have all of these areas of slightly higher density of dark matter and slightly lower densities of dark matter. And so once you start to get matter around, it's going to gravitationally be attracted to the places where there are dark matter. And that's how you start to get structure formation in the early universe.
Structures such as
Galaxies, yeah, so what would become a galaxy and eventually lead to star formation and eventually lead to the burning of the light elements into heavier elements that you need to create planets and eventually, humans. And so really, like, we wouldn't be here to study dark matter or anything if dark matter didn't exist or had way different properties than what we expect from our observations.
The universe is composed of a few different components, only one of which is the kind of, what we call baryonic matter, which is normal stuff, like us, what this room is made of, what the Earth is made of, all of the elements, things like that. That only composes a very small fraction of the total energy density of the universe. And as it turns out, is kind of outnumbered, 5 to 1-ish by another kind of matter that we don't understand, that doesn't, like to interact with, light. It really doesn't like to interact with things much or at all, except through gravity. And so we can see that using telescopes and a number of other methods to identify that there is some extra mass out there in the universe that's not the stuff we're made of. Now the hope is that we can actually detect that using, in a terrestrial detector, under the assumption that it interacts very rarely or weakly with the kind of normal baryonic matter that we're made of.
What is dark matter? We don't know what type of particle it could be. Some kind of composite object has been, for the most part, ruled out, so we really think it is some new fundamental particle. But given that we have, in the range of where a fundamental particle could live, that's something like 30 orders of magnitude. And we've, again, carved out, 3 here, 6 there, but there's a whole zoo of particles. For every different mass range, there's some different type of particle model that could populate that space and be the dark matter. And so really nailing it down and what that could be is what really drives me to keep doing physics.
Dark matter is kind of one of the biggest problems in physics today. Particle physics especially. We've, as a society, first identified that dark matter was a thing kind of in the early 1900s. So we really have not seen it interact with normal matter in a non-gravitational way for around 100 years now, which is a long time. So we finding it and seeing an interaction of dark matter in a terrestrial detector that we can conclusively say, these interactions are dark matter, would be groundbreaking. It would be the first time anyone has seen that conclusively, and it would help us work our way toward a more complete understanding of kind of the fundamental bits and pieces of matter and how they interact.
Couple things. One is that the alternative to particle dark matter is some modified theory of gravity. And personally, I haven't seen, and I'm not aware of any model of gravity that can reconcile all of the different observational signatures, dynamics of galaxies, dynamics of galaxy clusters, the large-scale structure of the universe, and the cosmic microwave background. The temperature and isotropies in the cosmic microwave background. Modified gravity can't simultaneously explain all of those things, whereas the cold dark matter paradigm does, with one model, reproduce all of the observed phenomena. In terms of looking for particle dark matter, yes, we've been doing this for maybe 2 decades now. Not traditionally, but historically, most of that effort has been focused in what's called the WIMP, weakly interacting massive particle space, which is, like I said, 10 to 1,000 times heavier than a proton, and we've had no luck there. That's right. But we don't know what type of particle dark matter could be, and to be consistent with observations of astrophysics, there's basically like 50 orders of magnitude where dark matter could live. And so that's a lot of parameter space to check, and we've carved out a good amount of the parameter space in the 10 to 1,000 GeV. So 1 GeV is about the weight of a proton. In that space, we've carved out significant space, but that's 3 orders of magnitude out of the 30 where it could potentially live. And so building sensitive detectors that can probe different regions of that parameter space is going to be key for eventually discovering the dark matter particle.
Dark matter really doesn't like to interact, and so it's not, when we detect, when we detect dark matter, it's not going to affect, my mom's everyday life, right? She'll be very excited that we found it, and she'll be like, "Oh, there's my boy," but it's not gonna have a direct impact on the lives of people today because it doesn't like to interact with what we see, right? But there, I would say, are two things that two caveats to that, right? So one, the search for dark matter is itself valuable. Finding dark matter is kind of a major milestone in understanding the universe around us. So that's the kind of academic answer. But getting there requires developing technology that doesn't exist yet, right? And so, for example, I mean, the work that we're doing, we're taking knowledge from the quantum science community and we're turning it on its head and trying to use it as quantum sensors for dark matter. But in the process, we are doing more research on the environmental interactions in these sensors that we can then turn back around and hand back to the quantum information community in such a way that they may be able to feed that into their design of their quantum computers, which then may lead to future kind of advancements in that field and in more direct impacts on society than knowing that there are a bunch of invisible particles that pass through us and exactly what they are, right? So there's really two different ways to see this. One is academic, like the hooray science moment, and the other is technology feeds forward into technology developed in the search feeds back into society. Yeah.
Even if dark matter, if there's no way to apply dark matter and harness its energy, which to me it seems like a long shot because of how, like, the challenge in detecting dark matter is how weakly it interacts with everything. And so maybe there's no direct application of dark matter, but the technology that we need to look for it and how we improve that technology and build more sensitive detectors can translate into many fields of industry. And eventually, developing quantum computers is something that will for sure impact everyone's day-to-day life. Maybe not in the next decade, but in the next 50 years for sure.
Huge portion of the matter content of the universe is dark matter. So by understanding dark matter, we know what the universe is made up of at the fundamental level. So this kind of addresses the curiosity, the fundamental curiosity we humans have. So that is really satisfying to understand our origin. And also, historically, what has been true is the application of dark matter or application of any particle, novel particle. Historically, what has been true is that its application follows its discovery. We find ways of utilizing it after it is discovered. Like if you look at electrons, protons, neutrons, their application came much later. It was not realized initially. And so the same probably will happen. We'll discover dark matter and then we'll figure out application that's going to revolutionize the world. So yeah, it has innately, it's satisfying to know our origins and what the universe is made up of to begin with.
Will this lead to teleportation devices? And I will say no with an asterisk, right? What is the asterisk? Well, an analogy I like to make for anyone who asks anything about whether dark matter will be useful is that right now, I don't think it's going to be useful. But if you think back 200 years, people didn't know that the electron existed, And now people are, have smartphones. People have all sorts of really high-tech stuff that allows them to do interesting things that people 200 years ago would never have dreamed of. And that scientists 200 years ago would have never attributed to the existence of an electron or the increased knowledge of an electron. So my asterisk is, I don't think so right now, but that is also because I'm a product of my time, which means that my knowledge is only based on what we currently know. And so maybe in 100, 500, 1,000 years, that picture may change.